Hello, this is my lab report for Lab 4, bar magnet. The purpose of this lab is to analyze the magnetic field produced by a bar magnet. Afterwards, we'll use a Glowscript model to visualize the field at different points. The main principles are the distance dependence of the field strengths and magnetic dipoles. A brief preview is that our magnetic dipole moment mu was 2.534 amp meters squared. Our principles revolve around different formulas for the magnetic field. So on the parallel axis of a dipole, we know it's Km times 2 mu over r cubed, and for a bar magnet, we know the field strength is exponentially proportional to the r, or the distance. And at the bottom, you can see a more general formula for the field at any point. Assumptions and reasonings. For the dipole formula, we'll assume that our distance is much greater than our dipole lengths. And for simplicity, we'll say that the only external field we'll have to account for is that due to the Earth. System versus surroundings. Our system will be the bar magnet, and our surroundings will be everything else, which includes the Earth. Initial conditions. For our lab, it'll depend on our bar magnet and our sensor. And then for our computational model, it'll depend on our given dipole moment and our distance. Experiment process. We'll start by aligning the meter stick on the east to west axis that's perpendicular to magnetic north, and then we'll also determine where the sensor is in our phone by moving it around until we get the corresponding max and min field values. Then for our parallel on-axis data, we'll determine the distance required for different magnetic field strengths, and we'll also do the measurement off-axis. Here you can see our photos and our data. So the magnetic field strengths that we were interested in measuring were 20, 70, 120, 170, and 220 microteslas. And you can see the corresponding distances. Here we can see our natural log graph. The slope in is about -3. Now we want to solve for the magnetic dipole moment, so we'll use our parallel magnetic field formula. And we'll set our r equal to 1, so that terms simplify out. And we can do some easy algebraic rearranging to get mu equals 2.534 amp meters squared. Now for the coding process. We start with physical constants, and by creating our magnet using our magnetic moment from the previous slide. Then we'll make a function that will calculate the magnetic field at any given point. And then finally, it's our visualization. So we put in a bunch of different locations, and then we'll calculate the field at those locations and provide a visual. Here's the output of our code, which shows the arrows of the magnetic field at different points. Note that this is a 3D visual, and so the Z arrow might look a bit bigger because it's technically out of the page and closer to the camera. Similarities and differences. So we found that our calculated parallel on-axis field was very similar to what we observed. It was pretty much the same. We also found that our field got stronger when we got closer to the magnet, and it got much, much weaker as we got further and further away. Some difference came in our off-axis 45-degree experiment, and we suspect that there must have been some outside field affecting our real-world experiment because it was multiple orders of magnitude different than what we calculated. Sources of error. One error could have been incorrect sensor positioning, but a really big one was the fact that there were magnetic fields that did not come from the Earth or the bar magnet. Inside the room, there were tons of smartwatches, laptops, tablets, phones, and just straight-up magnets or magnetic objects. Those things produce magnetic fields, which will heavily influence our sensor readings. What if we didn't orient our experiment to account for magnetic north? Well, then that means that we would have been measuring Earth's magnetic field as well. So that would have given us some incorrect calculations which do not accurately represent our bar magnet. What if we stuck two identical magnets together? Well, we'd expect our magnitude of our field to increase, and we'd expect our magnetic dipole moment to double. Conclusions. We found that our magnetic dipole moment had a magnitude of 2.534 amp meters squared, and our magnetic field strength decreases with distance. We also found that if we want to get precise and accurate lab data, we would have to really try to reduce our external factors or disturbances.